Intermediate Algebra, Section 2.6, the Algebra of Functions. We now examine 4 ways in which functions can be combined. And here in our class notes, we're given that if f and g are functions and x is in the domain of both functions, in other words, common to both of these functions, we can add the functions together into a new function. And where this first one came from was by taking the f of x plus the g of x. The new result of subtracting these two functions came from taking each of the original functions in the order that they're listed to result in that subtraction. Number 3, we can multiply functions together, which it would have come from multiplying each of those functions together. And f is showing that we can divide functions. This new function came from taking f of x divided by g of x with the stipulation that g of x is not equal to 0. We can't have 0 in the denominator, and something that we need to constantly be aware of and restricting domains if necessary. So let's take a look at how this works. In this example, we are given f of x defined with this rule and g of x, and they're asking us to add f of 2 plus g of 2. So they are evaluating the function defined by f with an input value of 2, which means wherever x is, we will put a 2 and simplify that. Multiplying, we get a negative 6 plus 1 results in a negative 5. So in place of the function when x, or the input value, is 2, the result is negative 5, so we can put a negative 5 in its place. They want us to add that to g of 2. And so we look at the g function, we replace x with a 2, or the input value of 2, and we will, wherever there's an x, put that 2. Following order of operations, 2 to the second power is 2 times 2, or 4, minus 2 results in a 2. So we have negative 3, and in place of g of 2 input, we get an output of 2, and we'll simplify that then. Now we have integers that we can add together, and our answer to this question gives us a negative 3. The next problem is asking us to express the rule for the difference of these functions. In subtraction, order is important, and they're asking us for what this looks like in this combined operation of subtraction. So where did it come from? It came from taking the g of x function minus the f of x function. We'll substitute in what those are. The rule for g of x is here. It is x squared minus 2. That's what it's equal to. So we're substituting our function notation for its equivalent. Minus f of x. In place of x, since it's equal to minus 3x, we can substitute that in. Now we have an algebraic expression that we're just simply going to simplify. We have subtraction of a quantity. I'm going to leave the first terms alone. Minus a minus gives us a plus 3x. Minus a positive 1 gives us a minus 1. Anytime you're subtracting a quantity, change the signs to the opposite of what they are and add. And we can simplify this further. The difference of these two functions, g minus f of x, results in the rule x squared. I'll put the 3x next, and a minus 2 plus a minus 1. When I subtract a minus 1, its equivalent is plus a negative 1, gives us either minus 3 or plus negative 3. The next function, I'm going to try and leave this so you can still see the rules, is asking us to divide the two functions. So to expand this further, they're asking us to take the function defined by f and divide it by the function g of x. And here's where we need to be concerned about our denominator and restrict our denominator so that we don't have a 0 in the denominator. We'll take a look at that in a minute once we get this simplified. The function defined as f of x is minus 3x plus 1, and g of x is x squared minus 2, and everything's fine. We don't need to simplify this any further. We can't simplify it any further other than restricting our domain so that we don't get a 0 in the denominator, which means we do not want x squared minus 2, the quantity in the denominator, to equal 0. Add a 2 to both sides, or take that minus 2 to the other side, makes it positive. And then to get an x by itself when it's squared, we'll take the square root of each side. And so this would be our restriction. Our domain can be all real numbers except x cannot be a square root of 2, and if you plug that in, square root of 2 when squared would result in square root of 2 times square root of 2, which leaves us a 2, and 2 minus the 2 is giving us that 0 in the denominator. So our domain could be all real numbers with that one exclusion of x not being a negative 2. This last example is asking us to multiply the two functions together, and the two functions are the same. So this translates into taking f of x times f of x. And up here you still can see this is what f of x was defined as in this problem. So in place of the function notation, we'll put the rule, negative 3x plus 1 times f of x. So we'll put it again. And there is what the product would look like. If you remember from previous algebra classes how to multiply two binomials together, we use the FOIL method by multiplying the first terms together, which gives us a positive 9x squared. The outside terms, which will give us a negative 3x. The inside, which 1 times negative 3x gives us negative 3x. And the last terms, which gives us a positive 1. Combine our like terms. Our final answer would be 9x squared minus 6x plus 1. In this next example, they're asking us to find the domains of the sum, difference, product, and quotient of the two given functions. When we're dealing with the sum, difference, and product, and the domain, we want all elements common, or the intersection to, in this case, f and g. All elements common to the two functions. So let's look at what our domain is of these functions. The only time we have to worry about a restriction on our domain is if the variable's in the denominator, don't see that in either one of these, or if our variable's underneath the radical. And that is the case with this function for f of x. Square root must be taken of a value 0 or greater. So our restriction must be that this quantity underneath the radical, called the radicand, must be greater than or equal to 0. That is going to be our domain. Solving for x, we'll subtract a 3 from each side, and we end up with x is greater than or equal to negative 3. So here's our domain for f. And if we put it in interval notation, our smallest value is negative 3. It's greater than, so it's headed towards positive infinity. We put our bracket because we're including the negative 3 in our solution, and infinity never has an end, so we put the parenthesis to indicate we aren't including an end value there. Here, for g of x, there is no variable in the denominator. There is no variable underneath the radical, so for our domain here, the domain will be all real numbers. When we're looking for a sum, difference, or product again, all elements common to these two functions. So let me do a number line just to talk about the domain of these two. Here we have negative 3 and greater, so we're headed towards positive infinity. This is the domain for the f function. The domain of the function defined as g of x is all real numbers, so it's headed to positive infinity just like the f function is, but also negative infinity, and we're looking for common, or the intersection. So it is this narrower domain that's defined for f of x. So the domain of the sum, difference, and product will all be simply x greater than or equal to negative 3, which is again that common domain or values between the two functions. Now, when we're looking for the domain of the quotient, it's also common to the two, but we need to exclude any value of x which makes the denominator equal 0. So let's look at what happens with the arrangement f of x over g of x. Our f of x is the square root of x plus 3, the rule. G of x is x minus 4. We want the common elements, so our domain is going to be this intersection of the two. So our domain right now is going to be negative 3 to infinity with one exception. So we're talking here in the number line, this would be the domain for the division, except we have to look for when the variable equals, the variable in the denominator causes it to equal 0. So we don't want that to happen. What will that value be? Take your denominator rule or expression, solve it for the variable. So we'll add 4 to both sides, and we end up with x cannot equal 4, because if it does, we would have 4 minus 4 is a 0. We would have a division by 0, which is undefined. So our domain is here, but it also cannot equal 4. And to clean this up a little bit better, we could use our set notation x such that here we are, this is what graphically it looks like, but when we get to 4, we have to exclude it, so we would put a open point and not include that 4. So to express that interval, we would say that it is x greater than or equal to negative 3 less than 4, or then continuing on, anything greater than 4 is going to work for our final domain. So there we have it using our notation. If we use interval notation, we are including the negative 3. We are not including the 4. So we would state, just like we had up here, negative 3 including, because of the bracket, to 4, parenthesis to show that we aren't, and then use the symbol union with, how do we describe this portion of our number line? It would be excluding the 4, so we'll put a parenthesis and then heading out towards positive infinity, and infinity does not have an end, so we put the parenthesis on it. Let's look at another example of combining functions when instead of giving a rule or an expression, they're already graphed for us. So in A, they're asking us to find f plus g of 4. Translation, that's f of 4 plus g of 4. Well, let's look at the graph and see if we can determine what happens when you have an input of 4 on your f function. So I have an input, which is my x, of 4, and what is the resulting output or y value? There's the point, and if I talk about the coordinates of that point, we're talking about 4, 3. So our output when x is 4 for the f function is a 3. Similarly, we'll do the same thing with the g function. When you have an input or an x value of 4, what is the resulting y? Here it is, the coordinates of that point would be 4, -1, so our y would be -1. Simplifying that, we end up with a result of 2. The second part of A is asking us to subtract the functions at 3, whoops, and there I go writing a plus, subtract g of 3. So f of 3, an input value of 3 means our x is 3. What is the resulting y? Where does it intersect? Up here on our graph, and we're at a y of 3. That point would have the coordinates 3, 3. So we will put its equivalent value, 3, minus g of 3. So our input or x value is 3. We go until we intersect this g function, and how high or what is the y output value? It is at 1. So 3 minus 1 gives us a value of 2. Next, they're asking us to determine the domains of f. Domains, whatever your technique is, whether you let it collapse down to the x-axis or whether you do your floodlights and look for where the shadows are, our smallest x value is here at 0 when we drop this one down, and continuously all the way here at 7. So in B, if we're talking about the domain of f, we would say x is greater than or equal to 0, less than or equal to 7. Interval notation, because we're including those, we would put 0 and 7. Furthermore, they ask us for the domain of g. Looking at g, it's starting here at 1 is the smallest x value it's using. Dropping it to the x-axis, we see the largest value it's going to is 5, so it would be expressed as x greater than or equal to, whoops, there I put a 0, it should be a 1, excuse me, less than or equal to 5. Interval notation, we could put that as a 1, 5, always the smallest value first, followed by the largest value. Then they're asking for the sum of the two functions, and when you're dealing with the domain of, whether it's adding, subtracting, or multiplying, it's all common elements to f and g, or the two functions, whatever their names are. So I'm looking for the intersection between these two, and because we've got our number line, what's common? Here, they intersect one another at 1, and they are using the same x's only to 5. It's the narrower of the two domains of the two functions. So This third thing that they're asking us in B is the domain of f plus g. So it will be the intersection of these two functions, or all common elements, and so we would list it as, in interval notation, 1, 5, or if we did inequality, we would say x is greater than or equal to 1, less than or equal to 5. Looks a little better this time. The last part of B is asking us for the domain of the division. When you are dealing with the domain and the operation is division, you want to exclude any value of which causes the denominator to equal 0. We want to avoid that. 0 in the denominator causes the expression to be undefined. So we're looking for G, when we're talking about the domain of f over G, we're concerned of where does G result in an output of 0. And that output of 0 is where it crosses the x-axis. Right here is where we have a 0 output. That's what we want to avoid, and it looks like it's falling right in between the two. We'll call that 3.5 would be the input value. Input value is the restriction that we will put on the domain. So it is 1 through 5 inclusive, with the exception of not letting x equal 3.5. So we could say this in one of two ways. We could say x is greater than or equal to 1, less than 3.5. We put the brakes on and exclude the 3.5. Union with, start right up with 3.5, and stop at less than or equal to 5. Interval notation, it would be 1 to 3.5, and because we're not including it, we use the parenthesis, union 3.5 to our maximum value of 5. We are including it less than or equal to, so we put the brace on it.